the microphone. So, first of all, in spite of appearances, it's not true that you need a British accent to give an in-person colloquium here. It's just so happening. We have many more in the future. There will be a reception afterwards. This will be the first time we have a reception after the colloquium since the beginning of the pandemic. And I'm very happy to present it today Professor Bobby Acharya, who is a professor at King's College in London, and he's also a senior staff member at the International Center for Theoretical Physics in Trieste. Professor Acharya got his PhD from Queen's College, London.
Queen Mary, yeah.
Queen Mary College. With Chris House was the advisor, and many of us know Chris, visited the department several times. Bob is maybe is at least the only string theorist that I know who is also a member of an LHC experiment. He's a member of the Atlas experiment, and he has founded the Atlas group at ICTP. It was there since the beginning. He will talk about, I must say that he has been maybe the person who introduced G manifolds with special holonomy and G manifolds in string theory, especially in the context of actually doing models and trying to extract information and constraints about particle physics. And he will talk today about M theory and the geometric unification of particle interactions.
Thanks, Massimo, for the lovely introduction. So, as I was telling the students earlier, these days in the field of particle theory, phenomenology, particle phenomenology, the approach is, the past sort of 10 years has been mostly sort of bottom up. And we don't hear so much about things like grand unification and supersymmetry and other mathematical structures. So I think it's good every once in a while for younger people in the field to be exposed to that perspective. And since I've been doing some work in that direction recently, partly thanks to Simon's collaboration on special holonomy in geometry analysis and physics over the last 5-6 years, I thought I'd share some of my thoughts on it with you today. So that's kind of the motivation. Massimo instructed me to sort of aim the talk at not just the department, but the first year graduate students. All right, so, and as hopefully most of us know, the fundamental physics of our universe is described extremely well, possibly, to me, sometimes it's like, I think it's ridiculously well by field theories. Visible sector matter is described by the standard model of particle physics, which is a Poincare invariant gauge field theory. And beyond that, gravity itself is also described by a field theory, Einstein's theory. Dark matter seems to be particular in nature, as far as we can tell. So it's presumably also described by a field theory. I'm going to talk actually about what's called M theory, and it's related children superstring theory. So, in my mind, M theory and superstring theory sort of arose as a natural mathematical extension of Poincare invariance. When you think about theories coupled that include gravity. So, as I was reminding the students, Haag, Lopushansky, and Sonius showed that the Coleman-Mandula, so-called Coleman-Mandula theorem, which you can paraphrase with the statement that the interactions, properties of the interaction of the S matrix for scattering of particles can only have, if it has symmetries beyond Poincare invariance, they're just global or internal symmetries. But what these fellows showed is that this is actually elegantly avoided in super Poincare invariant models. And sort of part of the standard law is that this is essentially the only way in which Poincare symmetry, on which this Lagrangian is based, can be extended in a non-trivial way. Okay, so that leads to supergravity theories, and supergravity theories are described by super algebras. This extension of Poincare invariance leads to an algebra called the superalgebra, and Nahm classified representations of these algebras that allow for particles with spins up to 2. But since we don't really know how to make much sense of spins bigger than 2, that was his motivation, and he found that there's a maximal dimension for which you can have this supersymmetry and gravity, and that is in space times of 10 space and 1 time dimension, so 11-dimensional space times, and that's the dimension in which, and that's the algebra, the symmetry structure which underlies this theory that's come to be known as M theory. And what is this M theory? Well, superstring theories are certainly theories in which you have gravitons, and you can calculate graviton scattering amplitudes consistently with in a framework which is consistent with quantum mechanics. And that in superstring theories, you do that. Superstring theories have a coupling parameter, which is the string coupling constant. So we normally study superstring theories that are defined perturbatively in this coupling. And in the sort of strong coupling limit, we get this 11-dimensional theory called M theory, which in some sense unifies all of the known superstring theories. And this picture sort of goes back to work in the 90s by Sen, Schwartz, my advisor Chris Hull, that Massimo mentioned, Paul Townsend, and Edward Witten. Okay, so I'm going to talk quite a bit about this M theory today. So I want to describe some of the things that we know about it. And first of all, I want to convince you that it's actually pretty simple. I mean, its basic physics is pretty simple. It has only 3 fields, unlike this guy that has, whatever it is, 45, 57, 60, or 50 or 60 fields. This has only 3. There's the metric, because it's a theory of gravity. There's the superpartner of the metric, and in this theory there are 2 superpartners of the metric. One is the Gravitino field. So the metric has spin, graviton has spin 2, quanta of the Gravitino field, so-called gravitinos, they have spin which is 3 is 1.5, so half a unit of spin less than the graviton. And then the spin 1 particle field, which is this C field. So what is this C field? The C field is just it's a generalization, if you like, of the Maxwell gauge field. So Maxwell gauge field has one index transported as a vector under the Lorentz group. This guy's called a 3-form because it has three. It's a tensor field with 3 indices, and it's totally antisymmetric in those indices. So just think of it as a generalization of the Maxwell potential. And at low energies and at the leading order, the symmetries fix the form of the interactions of this theory. And this so-called D equals 11 supergravity theory was discovered by Kremer, Julia, and Shirk, like 40 years ago. Okay, what do these equations look like? Well, basically, it's a generalization of the Einstein equations that you all have seen, Maxwell equation that you all have seen, and the Dirac equation that you've all seen. So I'm just writing these here schematically. So this is the Einstein equation, and the right-hand side is the stress energy tensor of this C field. So this equation and also this Maxwell type equation are going to play an important role in what we have to talk about today. So just think of it as it's just like gravity plus gauge field plus some fermions, but 11 dimensions. Now, that doesn't look terribly close to our world, which is described by this Lagrangian on my t-shirt. In particular, it doesn't look like there's any non-abelian gauge symmetry. The symmetries that that theory has are Poincare invariance, super Poincare invariance, and there's an abelian gauge symmetry, very much like the one in Maxwell's theory, but there's no, you don't see any gluons or W bosons in that Lagrangian. Nor do you see any chiral fermions. Fermions in this Lagrangian, only the left-handed particles coupled to W bosons. So the fermions are actually chiral. And for the rest of the talk, I'm going to talk about how this problem is actually resolved. At this point, you might have just given up. Actually, people did give up in the 80s working on this problem because for these reasons, basically. But the discovery of M theory, as I mentioned in the 90s, sort of revived interest in this problem. And these are non-abelian gauge fields and chiral fermions are building blocks of quantum field theory in 4 dimensions. And so it's really, so I'm just emphasizing that this is an important problem. The solution of this problem, so hopefully be able to convince you of, is elegant in my mind and involves some quite rich structures, in particular a rich geometric structure that involves very special kinds of singularities. These are going to be singularities in 11-dimensional space, but not just random. I mean, you'll see that they are very, very special. Okay, so to get us and some understanding of how this picture works, we need to understand a bit more the objects in this, the physical objects in this 11-dimensional theory. So as I said, this is a generalization of the C field is like a generalization of the Maxwell field in 4 dimensions. So if we were just, here I'm reviewing Maxwell's equations. And I'm writing it in form notation. So I'm suppressing the indices, to make things simpler. So F2, I've called it F2. This is the electromagnetic field strength tensor. Remember, it is a 2-index tensor with both indices are antisymmetric. F nu equals minus F nu mu. So that's why I call it F2, because it's got 2 indices. And the Maxwell equation tells you that you write it as d star F equals the current. And in this differential form notation, the left-hand side is a 3 form, so the right-hand side has to be a 3 form also. You can think of the current as a 3 form. The reason it's a 3 form is because particles, if you think of a particle moving on a line in our 3+1 dimensions, the world line of a particle is a codimension 3 object. You have to specify 3 positions just to say where the particle is. That's why it's a 3 form. So if I was just considering a completely localized particle, you have a delta function source, the equation would be, d star F is Q delta 3, or if I wanted to add magnetic sources, you also have a magnetic monopole in principle. So in M theory, we've got this 3-form gauge potential, so field strength is now a 4 form, and when you compute its equation of motion, the left-hand side is an 8 form, which means that it's sourced by objects of codimension 8, which means you have to specify 8 positions, 8 coordinates to specify the location of the source. So you should be thinking in 11 dimensions of a surface, a spatial surface, 2 real dimensions, which as it moves around in time, sweeps out a 3-dimensional spacetime embedded inside the 11-dimensional spacetime. And so in other words, the C field is sourced electrically by objects that are like membranes. Their spatial profile is 2-dimensional. Okay, and so these things are called membranes, or we usually call them M2 branes, M standing for M theory, and 2 because they're 2-dimensional. Okay, so we've learned something new about that we didn't know before, which is that this theory looks basically like Einstein, Maxwell, Dirac, except you don't have electrons, you have these extended objects. And you need, in order to understand the solution to the advertised problem, you need to understand the Einstein part, the Maxwell part, and how these objects enter into the problem, these membranes. Okay, so so the rest of the talk, I'm just gonna review the basic vacuum solutions of M theory in the sort of semi-classical limit, which is required to try to understand how we get from 11 to 4 dimensions. Then the the problem that I want to emphasize the solution of, I'll spend most of the time talking about, and then I'll sketch some sort of broad physical implications from all of this at the end. All right, so we have Einstein's equations. So in the same way, just if we think about general relativity in 4 dimensions, the simplest solution in 4 dimensions is the pure vacuum with 0 cosmological constant is described by just flat Minkowski space. So the same thing is true in 11 dimensions. You can just consider 11-dimensional Minkowski space, just a flat spacetime, as being the simplest solution. But you can also consider solutions in which some of the dimensions are curved. So I'm denoting in this talk, the extra dimensions are always denoted with an X. X for extra. And you have a metric on those extra dimensions, which is here called G tilde. And if you can, in the same way that the Ricci tensor of Minkowski space is 0, you can try to find solutions in which the Ricci tensor of this space is 0. And this equation, which is the vacuum Einstein equations without any cosmological constant, has a symmetry, which is that if you have a solution G tilde, you can multiply it by a constant, you get a new solution. That means that the volume of this manifold, the volume of your extra dimensions, is actually at this level a free parameter. So in particular, you can make X very, very small. And if you make it small enough, at long enough distances or at low enough energies, you effectively are working with a theory in lower dimensions. So in particular, to get to 4 dimensions, we want X to have dimension 7 and to be a small Ricci tensor equals 0, or so-called Ricci flat manifold. So that's what we're leading order. That's what we're interested in terms of studying the vacuum solutions of M theory are compact manifolds for which you can find a metric that has 0 Ricci tensor. Okay, I'll skip that slide. I'll do technical. And in fact, because of various structural theorems about Ricci flat manifolds, one is mostly interested in compact, simply connected Ricci flat manifolds. Now, constructing such manifolds is actually very hard. Yau won the Fields Medal for proving the Calabi conjecture, which allowed one to prove the existence of the first examples in the 70s. Now, all the known examples of such manifolds actually have what's called special holonomy group. And I'll tell you in a minute what the holonomy group is, but it is essentially if you take a point on your space and take a tangent vector at that point, and then you go around a loop and use the Levi-Civita tensor of general relativity to do that transport, the vector will come back to itself, but up to a rotation. And the set of all such loops generates a group of rotations of all these vectors. And that's called the holonomy group. And all known examples of these vacuum solutions, based on simply connected manifolds, preserve the supersymmetry that we talked about. So that means that the lower dimensional theory is actually a supersymmetric theory at leading order. And one might even suspect, since there are no known counterexamples have been constructed in the last 50 years, that these are the only possibilities. And that would actually imply that this theory, in some sense, in its geometric, in its low energy effective field theory description, predicts the existence of supersymmetry at some low scale. Okay, I said what?
Sorry, Bobby, should I ask a question?
Sure, yeah.
So here, by stable, presumably you mean you're including non-perturbative stability as a criteria?
Yeah, so actually...
So this is related to requiring to be simply connected in the previous?
No, it even includes non-simply connected. So for example, in this paper, I proved the conjecture for compact dimension 3. And that included, and the instabilities that I found for the potential counterexamples were non-perturbative, other than nothing instabilities.
So in complex dimension 3, you probably...
No, real dimensions.
Okay.
It's non-trivial even in real dimensions. We can discuss that later. So this slide here just gives you a picture of the basic properties of spaces with special holonomy. So a generic metric on a manifold will have generic holonomy group, which will just be the rotation group in n dimensions. But special holonomy corresponds to a holonomy group which is a proper subgroup of the rotation group in that given dimension. And these are the only possibilities listed here. And so this column I'm listing the dimension, I'm listing the holonomy group, these have names, and the last column I'm showing whether or not the manifolds have zero Ricci tensor or not. And so what you can see from this is actually there's two exceptional cases. One is in the case in the dimension of interest, which is 7 dimensions. There's a unique special holonomy group in that dimension, which is the exceptional B group of rank 2 called G2. And that one has zero Ricci tensor and, as I said before, preserves supersymmetry. So in the back of our minds, we're interested in these G2 manifolds. I haven't told you much really about them. I'm probably not going to tell you too much about them. So with that sort of picture in mind about what I sketched a bit of the mathematical structure of what the underlying the vacuum solutions. Let's go back now to our M2 branes that we introduced earlier. So we've got this small 7-dimensional manifold, which is our model of extra dimensions. And we've also got these membranes. Now, what about if I consider the membrane, the surface of the membrane, to be a surface inside my extra dimensions? So you can imagine, a sphere or some other surface, compact surface inside my extra dimensions. Well, remember, this X7 is small, very small. So if I look at it from this membrane from a long way away, I really would only see a particle, because its dimensions are sort of hidden in the extra dimensions, and we don't have a collider or a microscope big enough to excite the extra dimensions yet. So just to see that it looks like a particle, remember we had this generalized Maxwell field, C3. Well, if I integrate that field over that surface that the membrane is wrapping, that gives me, in 4 dimensions, a Maxwell field with one index, A1. And the equation of motion, this generalized Maxwell equation, actually becomes the Maxwell equation for a charged particle. So we've made some progress. We've now seen how to get electrically charged particles out of this system. However, this X7 is very small. And naively, if you just, you have the 11-dimensional theory has its own Newton's constant, which an associated Planck scale, which is typically we think of it as being pretty close to ordinary 4-dimensional Planck scale. You'd think that this particle is very heavy, but classically, the mass of this particle is proportional to the volume of the surface that it's wrapping. Now, naively, then, if the volume of this surface goes towards 0, the mass goes towards 0. And compared to the Planck scale, the electron mass is basically 0. It starts off life as being 0 before the Higgs mechanism anyway. However, we need to keep the we have to be able to collapse the volume of this surface whilst keeping the overall volume of X, even though it's small. We need to keep it finite because we want our Newton's constant to remain finite.
I get confused. In general, we would say intuition, the KK mode, the mass goes inverse to the dimension of the compactified space. Why here we say that scales like the volume?
This is not a KK mode, so you're absolutely correct. The KK modes do go like the inverse. But the mass of an object, the energy density in a soap bubble is proportional to the area of the bubble. This is the same thing.
Like the Gauss law.
It's because the membrane has tension, and if the cycle is incontractable, there'll be a minimal volume cycle for a given charge, and it will wrap that. Okay, now it turns out that these are extremely special situations, I'll try and convince you of, where you can vary the volume of certain surfaces inside X, whilst keeping the overall volume fixed. And in these special circumstances, this rough formula that I wrote down is actually, you can prove it's exact in the full quantum theory. So it doesn't just become an intuitive, general, hand-wavy picture. The picture I'm about to tell you of is going to be make some very precise statements. Okay, now in order to understand that, so when I was writing this talk, or when I told one of my students I was giving this talk, he sort of bet me to try and introduce the names of my academic father, great-grandfather, great-great-grandfather, and great-great-great-grandfather. I've done 2 of those already. These are the remaining 2. So yeah, in the context of ordinary 4D gravity, Gary Gibbons and Stephen Hawking wrote down some metrics describing so-called gravitational instantons.
So you weren't talking about Euclid?
No. You can work it out. Well, hopefully you can work out the other 2 that I've already mentioned. So yeah, so they were interested in solutions of the vacuum Einstein's equation. So again, you know, Ritchie flat metrics, but this time on 4-dimensional manifolds. And this was in the context of studying issues in quantum gravity in 4 dimensions. Whatever that means. And I thought we can describe this metric explicitly here, and the sort of mathematics involved with this is just Maxwell's equations type of stuff. So the metric depends on a function. Well, first of all, this thing here is a Euclidean metric in 3 dimensions. Okay. By the way, I hadn't mentioned Euclid at that point. This was the first time. So V is a function, which is basically the sum of Coulomb potentials in 3 dimensions. A, you can think of as a gauge field, which obeys the equation at the bottom, and tau is just a coordinate on a circle. And 1 over the function appears outside the metric on the circular part of the metric. Okay? And these Coulomb potentials are centered at points which I'm calling AI. So each of these AI is 3 parameters, and these are free parameters. So this metric solves the vacuum Einstein's equations for all values of these parameters. And what I want to do is give you a picture of what this thing looks like. Okay? So you have this circle, and then you have these 3 directions. And you see that the radius squared of the circle is controlled by 1 over this function. And this function is varying as a function of x. You can just think of this as a family of circles varying around as you move around in a 3-dimensional space. So away from the poles of the Coulomb potential, the manifold just looks like S circle times R3, basically. But what happens at the poles is that we're, 1 over the potential goes to 0 at the poles. So the circles at those points labeled by AI collapse at those points. Now you might think that that leads to a singularity, but it doesn't actually. If all the poles are distinct, that space is actually a smooth manifold, and that metric is a smooth, globally well-defined metric. So, I'm sorry for my poor artistry, but it sort of looks a bit like this near the poles. So if you've got 3 poles, A1, A2, A3, you can see going out away from the poles, you've got these circles that are growing. But between, and the circles all collapse at the 3 poles here. So in between 2 poles, the circle sort of starts at 0, it vanishes here, it grows for a bit, and then it collapses again. So this thing is actually a sphere. And if you've got n poles, there'll be n minus 1 spheres in the space. And they touch each other as indicated there. Now, as I said, when the positions of the poles are all distinct, everything's very smooth, but you can see that something weird has to happen if I say for example, send A1 equal to A2. This sphere will collapse to a point. And that's where we'll get a singularity. And these are the kinds of singularities that are related to the standard, the ingredients of the standard model. Yeah.
So it's just a very nice question. So here the volume also depends on the cross section. So it's not only depends.
Sorry?
Well, I mean the volume not only depends on the distance, but also depends on the cross section.
No, it's actually just the distance, yeah.
But I mean, but the cross section also has the you can shrink it.
there might be some pre-factor there, but yeah. But the essential dependence on the volume is this difference, is the distance between the poles. That's the crucial thing we need here. Now, so imagine, let's consider what would happen if we put all of the poles together at the origin, say. Well, then, the function just becomes n copies of n times the basic 1 over r Coulomb potential, and all of the n-1 spheres collapse to a point.
Sorry, Paul, just maybe a comment related to the question. I think his question is correct in the sense that I think what you write is the minimum volume. If you're talking about a volume associated with the same site in the homology class, there could be,
Oh, sure.
Yeah, I think that's why.
Oh, sorry. No, yeah, sorry if I misunderstood the question. So now, if you collapse all the spheres, something has to give, because in that limit, this space you can show becomes locally flat, in fact. So it just becomes ordinary, locally Euclidean space. But there has to be a singularity somewhere. Well, in a locally flat space, the only way you can get a singularity is if the space is not really Euclidean space, but Euclidean space divided by some finite group, by a discrete group. Okay. So, in other words, in that limit, the space becomes not just Euclidean, but Euclidean space up to identifications by some finite subgroup of the group of rotations. And in the case at hand, this is just the cyclic group of order n acting as rotations with angles 2 pi over n. So we have this, what happens is that we started off with this manifold X4, which is a smooth manifold, and it contains all of these spheres, and we've taken a limit in which it becomes this space here. Now this space here is actually singular, because the origin under any rotation is fixed by n elements. So you can sort of think of it as a cone with a conical singularity at the end. And that's the sort of simplest type of singularity that you can really have in this business. So, to give you a different picture, in the n equals 2 case, you've got a single sphere, you collapse it, you get the space that develops what we call a conical singularity. Now, remember our membrane. Our membrane wrapping this sphere looks like, as we said, an electron whose mass is proportional to its volume. Now, in this situation, the symmetries of the problem and properties of the Lagrangian tell you that this formula is exact. But the mass of that particle is the volume of that sphere. Okay, so now we've got a system that's got a gauge field, a massive charged particle, and plus its anti-particle. We've got particle of charge, say, +1, particle of charge -1, and we've got 3 parameters, the distance between the 2 centers. That's our system. And we also now know that when the 3 parameters go to 0, the 2 charged particles, charge +1 and charge -1, become massless. Well, that's described by, so the 3 parameters will be components of some, you'd think of them in the low energy theories as some scalar fields. Well, this system that I've just described is basically what we discovered at the LHC. It's just the Higgs mechanism for SU2. And what we learned from that is that these wrapped branes are actually W bosons. And this story continues for the general case. So for general n, you have n minus 1, 2 spheres. Now if you look at how those spheres are intersecting, their intersections are described by an intersection matrix. And that matrix is actually the Cartan matrix for the Lie group SUN. And this diagram is actually, in some sense, equivalent to the Dinkin diagram of SUN, for those of you who know about such things. So in this case, these M2 branes are actually gluons of an underlying SUN gauge symmetry. And more generally, this picture generalizes to other groups. So there exist vacuum Einstein manifolds associated to the groups SUN, SO2n, and also the exceptional groups E6, E7, and E8. And there's a very similar picture. And this group of identifications of R4 that give you the particular kind of singularity, conical singularity, the groups that appear are the finite subgroups of the group SU2, which arise in physics in many different contexts. They're closely related to point groups of crystals in 3 dimensions. And there's lots of other connections to other condensed matter systems. So this picture connects the finite subgroups of SU2, Einstein metrics on resolutions of singularities associated to these groups, and the thing that I was trying to convince you of, Yang-Mills fields, gauge symmetries, and the stuff that we were aiming for. So, when we go to quantum field theory class and we learn about the gauge symmetries and standard model and so on, and it's all beautiful. Its origins in M theory are somewhat remarkable, I think. So this picture also extends to fermions, fermion fields, which arise from additional singularities. And one of the reasons I wanted to give the talk was because we made some recent progress on this with Lorenzo Fosco. So if we just briefly go back to our bigger picture of these 7 extra dimensions, we've just said that the W bosons and gluons arise from these types of singularities. Well, near such a singularity, X would look something like a three-dimensional manifold times this singularity. And the fermions of the standard model in this picture arise from additional points on this 3 manifold where additional spheres collapse in very precise, in very particular ways. But I don't want to go into any of the details of that. So far, hopefully I've given you some sense that the basic ingredients of the standard model arise from these membranes in very particular singularities in vacuum Einstein manifolds, rigid flat manifolds. Now, if you then think about broader physical implications of this, then you sort of expect grand unification of fundamental interactions at some very high scale. Seems quite natural in this picture. Physicists talk about hidden sectors a lot. A lot of my colleagues here worked on hidden sectors in the context of dark matter and cosmology and other types of physics. Well, if you think about it from this perspective, one really expects a rich and abundant set of hidden sectors. So, for example, many different gauge groups under which you don't have particles in a standard model charged. The reason for that is that the singularities of R4 mod gamma are in codimension 4 and 2 which means they're localized in the extra dimensions along a 3-dimensional subspace. And in a 7-dimensional space, a pair of 3-dimensional subspaces will generically not intersect each other. So this already tells you that any interactions between, say, the standard model sector and the hidden sector, or any given hidden sector, will be sort of, what's called gravitationally suppressed. I mean, coupled gravitationally, mediated through interactions suppressed by the Planck scale. These parameters, these AIs, manifest themselves in the low energy theory as very weakly coupled scalars. They're very weakly coupled because actually they are zero modes of the higher extra dimensional Einstein's equations. And as a result of that, these fields would quite likely take over the energy density of the universe, the early universe, before Big Bang nucleosynthesis. These days, there's been a lot of interest in axion phenomenology and axion-like particles. These types of models predict lots and lots of axions, and so leads to this axiverse picture, string axiverse picture. Because the fermions of, say, the standard model are completely localized in the extra dimensions, the interactions between them, like Yukawa couplings, are all non-perturbative in this picture, which means that you expect, you generically have a large hierarchy between Yukawa couplings, which is something that we've observed experimentally by measuring the Higgs decay modes in different fermion, anti-fermion states. So that's the sort of broad. That's some of the broad physical implications. So I'll just conclude with some remarks, which is according to M theory, basic beautiful quantum fields that we work with in studying particle physics arise really from some rather rich geometric structures which connect discrete groups, conical singularities, and Einstein's equations. And I really find this picture quite remarkable, that this thing that we started off with, which is just Einstein-Dirac-Maxwell theory in 11 dimensions, gives rise to this structure. And knowing this can provide motivation for studying hidden sectors, new particles, and trying to have a framework for discussing early universe phenomena as well. So thank you very much.
So we can have questions from the floor and from the virtual audience somewhere over there. Yes.
We have a kind of a broad question. So can you compare with the F theory approach to modulability, which is also like we have to have work on this?
Yeah, I mean, it's
The
very,
advantage here that it's more geometrical. Or?
so Ethan's question was about a different perturbative corner. I was talking about M theory in 11 dimensions, but there's another corner called F theory, which is sort of type 2b, sort of non-perturbative version of type 2b superstring theory in 10 dimensions. There are a lot of similarities. There, one has one can construct the vacua more prolifically because you can use Yale's proof of the Glavi conjecture. There are a lot of similarities, although one thing that I would say is that F theory vacua are probably quite special in some sense. I have a sense that G2 vacua are perhaps more representative of what the stream landscape really looks like. That's just pure conjecture.
Well, questions get me.
So you have these dark sectors that pop out, and I'm interested in dark sectors.
Yeah.
Do you but you said gravitationally coupled. Do you see any sort of like situations where they're suppressed non-gravitational interactions?
Oh yes. But for dimension 4 interactions, so for example, U1 mixing, because it's dimension 4, even though they could be physically separated, just integrating out some very heavy bifundamental or something can generate a seismic interaction.
And that happens even with like anomalies and thresholds and everything being.
Yeah. I mean, if you're talking about hidden sectors which are, say, for example, say you have two SU5 sectors, and you integrate this thing out, then you get an additional suppression of, if you compute the vacuum polarization diagram, which is effectively what we have to do, you get additional suppression coming from the fact that you've got complete SU5 multiplets and approximate SU5 symmetry. So then you get very suppressed, much more suppressed than just a typical U1 prime. And there's probably other interactions that I'm not remembering.
So I have one question following Neil's question. So for the kinetic mixing between U1 and U1 prime, so are there any so is this interaction suppressed?
Are they what?
Is this interaction suppressed or not?
No, it's because it's renormalized. It's because it's renormalizable. So the
so as long as we have
it's only logarithmically sensitive.
So as long as we have some bi-charged fermion, and then we can just get.
You have a heavy bi-charged fermion. You integrate it out. And
I have another question. Is you mentioned that we can make the analogy of the Higgs mechanism by just turning the distance between two singularities. But I'm just confused about one thing, because what we have learned from so just some traditional thought of the breaking or traditional thought of the Higgs mechanism is we in the early time have some thermal we have some small correction which will make the potential to be like this, and then once we're going to use them, we have how to relate to this code, how related this.
Well, so the Higgs fields I was talking about there are probably, those ones are probably not this one.
Oh, okay.
This one is probably just a super partner of one of those localized fermions I was talking about.
Other questions? So I have one question is, how does chirality arise in this computation?
That's an excellent question. It arises from, so you have this gauge field, which is in codimension 4, so it's actually supported along this Q3 manifold times our 4-dimensional space. It's a 7-dimensional gauge field. And if you look at the interactions of this system, you can see there are various Chern-Simons type terms that when you have this additional localized chiral fermion, localized singularity, and you compute these interactions, essentially you get the anomaly polynomials of ordinary 4D gauge theory. So it's a subtle, it's a sort of subtle computation, but it's essentially the anomaly inflow mechanism that allows you to see you have chirality, even though it's in an odd-dimensional space, which is sort of surprising.
And is this chirality, do you have various sectors and then various chiral sectors, and then the anomaly cancels when you sum over all of them?
Yes. Yeah. So if you're interested in reading about that, Ed Witten had a paper called Anomaly Cancellation in G2 Manifolds, where he explains all of this in the early 2000s.
Other questions? I have another small question. You had simply laced groups. Is there a fundamental reason why not simply laced, the SON for an odd, for instance, not appear?
Yes, it's intimately linked with the classification of these singularities, which are in one-to-one correspondence with the finite subgroups SQ2. However, you have this 3-manifold Q3 on which this thing is supported. If this thing is non-simply connected, you can imagine situations in which, as you go around non-trivial loops in that 3-manifold, that you get an automorphism of that singularity, and that effectively allows you to have vacua with other groups.
Thank you. So, if there are no other questions, let's thank Bobby. We can continue our discussion on the 8th floor of the cheese and wires.
Thank you. Down there or is it down there?
It's 71.
It's CSMR.
I believe so.